Welcome back, AP. 19.6. Can we predict if something is thermodynamically favored? Looking at delta H and delta S without calculating. And then how will temperature affect it, as in if temperature increases or decreases? So we have two big learning targets here. Explain whether physical or chemical process is thermodynamically favored. And then explain the relationship between the solubility of a salt and changes in enthalpy and entropy when you dissolve a salt. Okay, so let's do the first one. Temperature conditions for a process to be thermodynamically favored, remember we want it to be less than 0, can be predicted by looking at the signs of delta H and delta S. Okay, so there's a chart down here. We're going to look at the chart more in detail in just a second. Okay, right down here. Okay, but the key is that's what we want. Okay, we want exothermic, okay, because remember it's easier to lose heat than gain, and we want disorder. Okay, so it will be thermodynamically favored at every temperature. That's what we want. However, if these values go above 0 or less than 0, then they're only thermodynamically favored at high or at low. Okay, so in cases where delta H is less than 0, that's good, and delta S is greater than 0, no calculation of delta G is necessary to determine if it's thermodynamically favored, because this means that they are both driving, you're going to hear me talk about that in just a second, driving the reaction, okay, to make it thermodynamically favored. In cases where delta H is positive, which means endo, and delta S is less than 0, which means you're creating order. You have less movement. No calculation of delta G is necessary to determine if the process is thermodynamically unfavored. So that means neither one of them are driving the reaction because it's not thermodynamically favored. Now, I have a picture in the notes to go with this one about the dissolving of salt, the dissolution of salt. Gibbs free energy for dissolution, which means it's a fancy way of saying dissolving, of a substance reflects the number of factors. Breaking, intermolecular forces, okay? And most of the time, the intermolecular forces that you're breaking, and I'm going to put them over here, probably some ion, oops, go down there, ion dipole, because remember, it's a salt dissolved in water. You may be breaking some hydrogen bonds when it comes to the water, but this is the key one because remember with salt, Na and Cl, this Na is attracted to the oxygen part of water and the chlorine is attracted to the hydrogen of the water. So this right here, that's ion dipole because you have an ion attracted to a dipole molecule. Okay, all about chapter 11. Okay, so the breaking of intermolecular forces that hold the solid together, the reorganization of the solvent around the dissolved substance. Okay, so this is the ion dipole part, and the interaction of the dissolved species with the solvent. Okay, so this is all intermolecular forces, and it's all about ion dipole. Okay. So it is possible to estimate the sign and size. So remember when they say magnitude, the size of the number of the enthalpic, I've never even said it like that before, but enthalpy and entropy contributions to each of these factors. However, making predictions to the total change in Gibbs free energy can be challenging due to the cancellation among the free energies associated with these three factors. Okay. So with these two learning objectives, it's about predicting. Can you predict if something is thermodynamically favored looking at delta H and delta S at certain temperatures? Okay. So the sign of delta G tells us thermodynamically favored. So we just focused on delta G equals delta H minus T delta S. This would be not standard state. Or if it is at 25 degrees Celsius, we just put those little degree signs. And then now temperature, okay, so remember that temperature will be at 298. This temperature could be at any temperature, okay? So I have a table, and it's the same table like Doc Dina has up here, okay? So this table, we want thermodynamically favored. And we want thermodynamically favored at every temperature. So we already know we want delta H to be negative, okay, which means exothermic. We want delta S to be positive because that means we're creating movement. And delta G, thermodynamically favored, but at every temperature, okay? So that means in this case, both are driving the reaction. You can have one of them only driving it, and then you can have neither of them driving it, okay? So my kind of trick to you, you got to know this chart. You got to be able to predict, okay? If you notice this one, I'll put it in a different color. This scenario versus this scenario, okay? They're opposites of each other. If delta H is negative, it's exo. So if it's positive, it's endothermic, okay? Not driving the reaction. If it's negative, that means you are creating order. So if these are opposites in signs, okay, then your delta G is going to be opposite of sign. So not thermodynamically favored at all temperature, okay? So if these two, what I like to remember is I like to remember this first column, because then I know the second column is just the opposite of sign for all variables. Okay, so if my H and my S are opposite of signs, I know my H is correlated to delta G. Okay, so if my H is negative, I know my delta G is going to be negative as long as delta S is positive. Okay, so it's a trick that I use. So I don't need to memorize the second one because I just know it's opposite. If H is positive, S is negative, then that means this H is correlated to that delta G, which means it's also going to be positive. Okay, next I look at the third scenario. Okay, and actually let me go back and write on this scenario. Okay, I'm going to put right here, neither H or S driving the reaction because it's not thermodynamically favored, okay? So now here's the next scenario. I like to remember this third one. What if your H and S are the same sign, okay? So your H and S, same sign. And we already talked about here when they're opposite. Well, H is negative. That's exo. That's good. Okay, so I'm going to put a little happy face. That means it's driving the reaction. So I'm going to put a little happy face right here. Means driving the reaction. And just so you understand what that means, is driving the reaction means that it's helping the reaction to become thermodynamically favored. Okay? But your S is negative. That means you're creating order. You're creating less movement, not driving the reaction, okay? So now you have two possible answers. Your delta G could be positive or negative, okay? So remember, if our H is negative and our G is negative, okay, which means thermodynamically favored, it will only be thermodynamically favored at low temperature, okay? And this is going to be due to delta H driving the reaction. What we mean by low temperature is usually something less than 298. So I'm going to say temperature. Sorry, every time I write in these charts, it does not like me writing them. The temperature less than 298 Kelvin. Okay. If I know that scenario, then I know the other scenario is just opposite. Okay. And then one more time, if delta G is positive, then that means it's not thermodynamically favored, but now at high temperature, okay? So they're just opposites of each other. I know the first line and I know the green line because I know the other rows, they're just opposite. So if this is positive and this one's positive, okay, this means it's endothermic, not driving the reaction, but this is positive. I'm creating disorder. So this case, this is driving the reaction, okay? So I got another two scenarios type of bit. Okay, so if it's negative, thermodynamically favored, we'll look right here. If it's thermodynamically favored at low temperature, well, in this case, if they're both positive, then it's thermodynamically favored at high temperature, which means we're talking about temperatures very high, higher than 298 Kelvin. Okay, when I say know this chart, ladies and gentlemen, know this chart. Okay, So what is driving the reaction to become thermodynamically favored? Okay. Right here, this learning target number 2, the dissociation of salt. Okay, I know you've seen this picture before. It depends on temperature. Okay, so say I have a salt. Okay, and let's just say it's sodium chloride. Okay, so I have my sodiums get smaller because they lose electrons, and chlorine gets bigger because it gains. Let's put this in different colors. So these blue ones, probably the chlorines, okay? And then the little blue ones are the sodiums, okay? So when this dissociates, I'm breaking a solute. Remember, the solute is what is dissolved. What got dissolved, okay? So now I have something dissolved. I now have ions. And now I have water, okay, H bonding. And by breaking up that solvent, I have to also break hydrogen bonds, okay, the strongest intermolecular force. So my solvent is who dissolved it. Okay, so now I have water freely moving about because I broke those intermolecular forces. So this right here, those dotted lines, that's the H bonds, the intermolecular forces that were broken. Okay, so in this case, my delta H, if my delta H is positive, endothermic, which is not thermodynamically favored. Okay, but my delta S is positive because I'm creating movement. That's a good thing. That means he's going to help me drive the reaction. So remember, if they're both positive, that means we got 2 scenarios happening, okay? So remember, if they're both positive, we have 2 scenarios. So that means it will only be thermodynamically favored at very high temperature. When you actually plug the values in, you would actually see that it's going to be positive because this is positive, temperature is positive, this is positive. When you take a positive number minus another positive number, it's going to still be positive, okay? So think of Le Chatelier's back in chapter 15.7, okay? If you increase the heat, okay? So remember, we said this is delta H. We said it's positive. We said endo. Remember, you have to think of heat as a reactant. So if I crank up the temperature, here comes my teeter-totter, I crank up the T, I crank up the heat, endothermic reaction is going to shift to the products. I have to make more products. And by making more products, I had to lose some reactants. So that means it's going to be thermodynamically favored in the forward direction to produce more products. But what did we also talk about in chapter 15? K gets affected. Okay, only time K gets affected is with temperature. Now, how do you know what K is going to do? Well, remember, K is products over the reactants. If I'm producing more products, my products are getting bigger and bigger and bigger. I'm becoming a bigger number versus a little tiny little small number. Big number divided by small number, my K is going to increase. Okay, so remember these tricks that we did in chapter 15. Okay, so now I form ion dipole. Okay, so now I took my broken salt, okay, my broken NaCl's, okay, so let's go ahead and label those. Those were the NAs. And my Cl's are the big ones. And here comes my water. And now this is basically the dissolution of salt, okay, aka dissolving salt. So notice when they come together, my chlorine is attracted to the hydrogens, okay, and they didn't draw the little dotted lines, but remember you would have these little dotted lines with each hydrogen, just one hydrogen on each water molecule. And then I get my Na plus, and my sodium is attracted to the oxygens, okay, and that's why we call it ion dipole. In this case, my H is negative. That's a good thing. That means it's exothermic, okay, so that is driving the reaction. But my S is negative, okay, because remember, I am creating order, and that not thermodynamically favored, okay. So what if they're both negative? Well, it's like the same scenario. So up here, if they were both positive, it was thermodynamically favored at high. Well, if they're both negative, then it means thermodynamically favored at low, okay? Because remember, you have a negative number minus T times a negative number. Now you're thinking, okay, a negative and a negative, that's going to become positive. But remember, delta S is joules over Kelvin. We have to convert this to kilojoules per Kelvin. So even if this said like 100 joules, it's now going to be 0.1. Okay, and you're putting a very tiny number inside of there. Okay, so that's why you have to be able to do both ways. Can you see it without actually plugging it in? And can you predict? And then obviously the easier way is calculating. So now if my delta H is exo, that means my heat is a product. So if let's just say I decrease the temperature, okay? So remember, this is what my teeter-totter looked like. There's my temperature, and now I decrease temperature. That means I'm losing heat. I'm losing heat. My products are losing. So with an exothermic reaction, I'm still going to shift, okay? But I still need to produce more products because I have to shift my equilibrium and produce more products. So what will happen to K? Well, here we go. So my K, products over the reactants. And if I have to produce more products, my products are getting bigger and bigger and bigger. So that means my K is going to increase. Well, what if I think of the opposite? If I still got heat, but now I said my temperature increases. So now my temperature, my products are dominant. Very, very dominant. So to reestablish equilibrium, I got to make more reactants, lose products. So an exothermic process towards the reactants, okay? This is not going to be favorable because products are the reactants, okay? My reactants are getting bigger and bigger and bigger, which means my K is going to increase. So remember what we said right here, favorable at low temperature, okay? So if it's favorable at low, that means temperature is decreasing. It's not favorable at high temperature. So that means the temperature is increasing, not favorable. Okay. So if you know that trick, that little chart, it's going to save you a lot of headache. Okay. So AP tip before we do a sample practice problem. What's driving the reaction? Okay. So all you need to do is focus on your delta H and your delta S. Okay. So if it's enthalpy only, okay, enthalpy only means, remember, thermodynamically favored reactions, we want exothermic, okay? We want our delta H to be negative. And that means our delta S is negative. It is not driving the reaction. If our entropy is driving it, that means we have movement. We have motion. We have dispersion, okay? So that means our delta H is positive. Endo, that ain't gonna happen. And in a happy world, we would get our enthalpy to be negative, and we would get our entropy to be disorder, chaos, dispersion. That would make both of them thermodynamically favored. So focus on your H and your S, who's driving the reaction, okay? So let's bust out a calculator. Let's practice, okay? The Haber process, remember the Haber process is the famous way of making ammonia. I got N2, 3 hydrogens, made my 2 ammonia. Assume my H is negative. All right, that's a good thing, exothermic. And my S is negative, okay? My S is negative, that means I'm creating order, okay? Assuming that the temperature is not changing. What is driving the reaction, okay? Well, since my H is negative, and we'll say, and delta S, with the little degree sign, is negative, enthalpy is only driving the reaction, okay? Now, can you predict when it will be thermodynamically favored? So the reaction will only be thermodynamically favored in the forward direction When is it high temperature or is it low? It's not an all temperature scenario because they're both negative. So since H is negative and S is negative, that means my delta G, it's going to have an either or, a positive or a negative. So a positive, we know it's not thermodynamically favored. Negative, thermodynamically favored. So I know we don't have this memorized yet, okay? Or AKA we learned it. So go back to scenario when they're both negative. They're both negative, thermodynamically favored at low temperature, okay? So before we calculate, let's predict, okay? So now that we predicted what's driving the reaction, it will only be thermodynamically favored at the low. So let's calculate delta G at 25 degrees Celsius and at 500, okay? Now, usually AP would say, assuming delta H and delta S are not affected by temperature. Now, why do they have to say this? Because remember those appendix values, the tables that they give you? The appendix values for delta H and S and delta G are all standard state. 298, okay? We would have to have a brand new table for 500 degrees Celsius. So that's why AP would say, assume that H and S aren't affected by temperature, then I can use the same values for H and S. So use the same H and S for any temperature, okay, as long as they say that. All right, so at 25 degrees Celsius, okay, we have our delta G, delta H, and like I said, get those calculators out. Always check Rodriguez's math, okay? So we have our H up here, negative 9238 kilojoules per mole. We know temperature is 298, okay, because remember that's 25 degrees Celsius. Now remember, beware of the units for delta S. We have to convert them. We got to convert these joules into kilojoules. So negative 198 is going to become point, and it's still negative, 1983 kilojoules over K times moles. Okay, so now I'm going to put that negative in there, 0.1983 kilojoules moles times K. So let's plug this in. Take care of the temperature and delta S first. So 298 times that negative 1983. So this part right here stays negative. 3 sig figs, 59.0. Our Kelvins cancel, and then I get my kilojoules per mole. Okay, so I'm going to take my negative 9238 minus that negative number, which becomes positive. Oops, kind of helps if I'm plugging in the numbers right. See, I told you, you got to check my work, okay? So that means my delta 8 or my delta G is going to be, now I have subtracting. So I have 2 sig figs here versus 1, so which means my answer is only going to have 1 after the decimal. So negative 33.4 and then kilojoules per mole, okay? So is this thermodynamically favored? Yes. It is thermodynamically favored since delta G is negative. Now the question is it going to be thermodynamically favored at high temperature? Well, remember, we just predicted it's only going to be thermodynamically favored at low. So when we get to 500 degrees Celsius, okay, this predicting, should not be thermodynamically favored, which means my delta G should be positive, okay? So that's why knowing that chart is going to be very helpful. So my H and my S aren't going to change. Now I just made a little boo-boo. I caught myself. Because it is not standard state, we got to take these little degree signs off. Okay, so I'm going to make a note. Since it's not standard state, I'll just put right here, no degree. Okay. Still calculate the same way. So I'm going to get negative 9238 kilojoules per mole. And then minus, now I got to take this 500 and I got to add it to 273.15. Because that was only, I'm gonna change this to put a decimal right there to keep 3 sig figs going. 773 Kelvin. And then my delta S is still the same, negative 0.1983 mole.K. Okay, so let's take care of the temperature. So 773 times negative 0.1983. So this part right here, I'm still going to get a negative 3 sig figs, negative 153 by K. So kilojoules per mole. Okay. If by chance you round that last digit, like this one right here, when it came into the calculator, I think it was like negative 59.0, like 8 or something. You can change this to 1, because remember, that last digit you can be off by 1. It's not a big deal. My answer key said 33.3. I got 33.4. We're all good. Okay, let's don't stress about the rounding. Only stress about the sig figs. Negative 92.38 minus that negative 153. So I got a negative, and then that negative and negative are going to cancel, but this 153 is higher than 92. So I know I'm going to get positive here. And because 153 has nothing after the decimal, I'm going to get positive 61 kilojoules per mole. And definitely not thermodynamically favored. Okay, so what of your observation as temperature increases? So as temperature increases, okay, the forward reaction becomes not thermodynamically favored. Okay, so as it gets higher and higher and higher, it's becoming less thermodynamically favored. Okay, you can abbreviate temperature, you can abbreviate thermodynamically favored. Okay, we'll see you on the last one.